Hey guys, so for my group's project, we did projectile motion. And what we did was we took this Nerf gun and we shot it at a 45-degree angle. And here's its trajectory path. And so what we're going to be looking at is an energy lens. So how the spring potential energy of the spring in this gun turn to the kinetic energy of this bullet, which is a regular Nerf bullet, but we taped it to increase its mass, so it wouldn't go as far, but also so you can see it better, so it's bigger and there's a good red color. And so we'll also be analyzing the energy transformations that occur in its trajectory. How right here, for example, has the most potential energy, and right here it's all kinetic energy. So this whole energy transformation process all starts out with the spring potential energy of the gun. And we define spring potential energy as half kx squared. So to get the spring potential energy, we are equaling it to the initial kinetic energy. And we're calling the initial kinetic energy the kinetic energy of the bullet as soon as it leaves the gun. So we know the mass of the bullet, 5.4 grams. So in order to figure out the spring potential energy, we need its kinetic energy. So we just needed to figure out its velocity. And so this is how we figured out the bullet's velocity. So from that video, how we figured out the bullet's velocity is it took the bullet to go across the 6-foot board in 0.3 seconds. We figured this out because it left the gun at 41 frames and it crossed the end of the board at the 50th frame. And so we could, with tracker, we converted that to the change in time. So we found that to be 0.3 seconds, and it went 6 feet. And all velocity is change in distance over change in time. So we got 6 feet in 0.3 seconds to equal 20 feet per second. We converted that to meters. We got 6.1 meters per second. So now we can use these. Now we know the velocity. So we can, first of all, we can figure out the kinetic energy. Through these calculations, we get the kinetic energy to be equal to 0.1 joules. So if we're saying that these two equal each other, 0.1 joules is equal to half kx squared. So, and we know the distance the spring travels because we measured. So this is the resting point of the spring, and then this is how much it pulls back. So we measured this distance to be 0.043 meters. So 0.1 joules is equal to half k 0.043 meters squared. Through this we get k is equal to 108.2 Newton meters. So now we're going to be looking at the energy transformation of the bullet's path through the air. So right here, it has a maximum height. So that means its potential energy is the greatest. So we can figure this out by breaking down its velocity vectors into components. So this is when I shoot the bullet right there at 45 degrees. And so the two legs of this triangle are 4.3 meters per second. So then we can, this is disregarding this 2.3 meters right here. Because we know that this initial potential energy is 0.12 joules, because it's just the mass of the bullet, 5.4 grams, times the height, times gravity, 2.3 meters. So essentially this maximum potential energy is going to be this one plus this one up here. So to get this one, we know that it's going to be equal to the initial vertical component of the kinetic energy. So we can set them equal to each other. half m v naught squared is going to be equal to 0.05 joules. We just add, so that's this potential energy right here, plus the initial potential energy is going to be equal to just these two added together right here. So that'll be 0.17 joules right there. And so that means we know that the vertical component of the bullet's velocity vector at this point is going to be, its kinetic energy vector is going to also be 0.17 joules. But it's also going to have, coming down, it's going to also be going this way at a certain velocity. We figured out the maximum potential energy, so now we're going to figure out the maximum kinetic energy, also the end of the path. Is when it has the most kinetic energy, because all of its potential energy has been converted into kinetic energy. So we know that the horizontal vector component of its trajectory is going to be equal to the velocity we get from its potential energy being converted into kinetic energy. So 0.17 joules equal to that. We find out that its velocity is going to be equal to 7.9 meters per second. And we know that its horizontal velocity vector component does not change throughout because we're neglecting air resistance. So now we're just wondering what this net velocity is. So we just use Pythagorean theorem here, find out to be 9 meters per second, and that way we can figure out the resultant kinetic energy, which is just plug that into half mv squared and we get 0.22 joules. So now what we want to do is we want to find out the maximum height and the range of the trajectory of this bullet. So to find the maximum height, we're going to look at the potential energy max, which we figured out in the last segment to be 0.17 joules. We know that potential energy is mgh. So 0.17 joules is equal to mass, gravity, height. Solve for height. We get the height to be 3.15 meters. So, and this was our initial height that we shot the bullet from. So this is just the height in between these two, total height right here. Now to figure out the range, we need to look through a kinematics lens. So we're going to use this equation. Velocity equals initial velocity plus acceleration times time. So what we did was we broke it. So we just broke it into just this half, just from when the bullet is here to when the bullet is here. How long did that take to fall? So we know initially the vertical component of velocity for the bullet was 0. But then here, when we broke up the velocity into components, the vertical component was 7.9 meters per second. We know that 7.9 meters per second is equal to u, which is 0, plus acceleration times time. Acceleration is gravity. Solve for time, we get that this from the bullet to go to here is 0.79 seconds. So now we just need to know how long does it take the bullet to get from here to when it had maximum potential energy, the height of its trajectory. So again, we use this equation right here, v equals u plus at. We know that the velocity here, the vertical component of the velocity, is 4.3 meters per second. And then the initial velocity is this, and the final velocity is that. So that would be 0 is equal to 4.3 meters per second plus 10 meters per second squared times time. So negative 4.3 meters per second is equal to 10 meters per second squared times time. So that means time is just going to be equal to, we're not going to have negative seconds. So that's just going to be 0.43 seconds. This is only this way because I called down the positive velocity direction. So that means up was the negative. That's why we're getting a negative here. Total. So we know that from here to here, it takes 0.43 seconds. And then from here to here, it takes 0.79 seconds. So the total time is just going to be those added together, which is 1.22 seconds is the air time.
So to get the total displacement, horizontal displacement, the range, displacement is just equal to velocity times time. Spend the velocity, the horizontal component of velocity, which hasn't changed the whole time because we neglected air friction. So velocity times air time, and we get 5.25 meters. Now, in our actual experiment, we measured the displacement, and that was 15 feet. So this was our actual range we got in the experiment, and it's less than this one due to air resistance, air friction. So we can see that because of air resistance in our experiment, it prevented the bullet from going roughly a little less than 3/4, just about 3/4 of a meter. Yeah, that's that.